The topic of our first lecture is series. Actually, it will be topic for our next several lessons. Let us consider a sequence AN, which consists of elements A1, A2, and so on, AN, and so on. And we will call formula sum n from 1 to infinity AN, which is A1 plus A2 plus A3 plus so on. We will call this formula a numerical series. A1, A2, A3 and so on are called elements, and if we write down the formula AN, which is f of some number n, this will be general element of series. We may shorten this denotation as sum AN. How do we add this infinite number of elements? We have partial sum Sn, which is A1 plus A2 plus so on plus AN. Or we can write it down as sum k from 1 to n of AK. So this sum will be is partial sum plus some remainder. So sum n from 1 to infinity of AN will be Sn plus some Rn. And this Rn is an plus 1 plus an plus 2 plus so on. So if we have a sequence of partial sums, then we'll have S1 will be A1, S2 will be A1 plus A2, S3 will be A1 plus A2 plus A3 and so on. Sn will be A1 plus A2 plus so on plus An, and this tends to infinity. So if we have this sequence S1, S2, S3, SO, Sn, S and so on, we can take limit when n tends to infinity of Sn, and we call this number sum of series. So S will be sum n from 1 to infinity of An. This is how we calculate sum of the series, and if this limit exists, if this number is finite, then we say that this series converge to this number S. So if limit n tends to infinity Sn is less than infinity, then sum n from 1 to infinity An is convergent. If not, we tell that it does not converge. Let us introduce one more series. A plus AQ plus AQ square plus AQ cube plus so on plus AQ power n minus 1 plus so on, which can be written as sum n from 1 to infinity AQ power n minus 1, where A is non-zero. This series is called geometric series. Similar to geometric progression, actually, these elements are elements of geometric progression. Partial sum will be A minus AQ power n divided by 1 minus q if q is not 1, or na if q is equal to 1. So If this multiplier q is less than 1, then limit n tends to infinity, q power n is 0, so limit n tends to infinity, Sn is a over 1 minus q. If absolute value of q is greater than 1, then limit n to infinity, q power n is infinite, then this series won't converge. If multiplier equals minus 1, then we will have a minus a plus a minus a plus a and so on. So we'll have that s2k as 0, s2k minus 1 equals a, so limit n tends to infinity Sn won't exist. If q is 1, then we have a plus a plus a plus so on to infinity, so limit n tends to infinity Sn will be infinite, so series won't converge. So we will have only one case of convergence, only one case from 4 considered when this series converges. So sum n from 1 to infinity a q n minus 1 is a divided by 1 minus q when q is less than 1 by epsilon value, or infinity when absolute value of q is greater or equal 1. This series won't converge if we have other case than this one. There is a classical Greek paradox, ancient Greece paradox, that was formulated by Zenon of Ilia, and this is one of his most famous paradoxes. So, what's the idea? We have running Achilles and running turtle, and Achilles won't be able to chase the turtle down. So we have, for example, 1000 meters between Achilles and turtle is 10 times slower than Achilles. So when Achilles runs for the turtle will run from Achilles. When we will have initial distance, we'll have 1000 meters between them. Achilles will run this 1000 meters, but during his run, turtle will crawl for 100 meters. Achilles will run these 100 meters, but turtle will crawl for 10 meters more. Achilles will run this 10 meters, turtle will crawl for 1 meter. Achilles will run this meter, turtle will crawl for 0.1 meters, and so on. So Achilles won't be able to catch this turtle. Is it true or not? Actually, we have to take into account interval of time that's required for Achilles to follow the turtle. So let us have this distance 1000 meters, and this distance Achilles runs during time t1. Then if our turtle is 10 times slower than same distance, she will crawl for t1 over 10. So what time will Achilles run chasing the turtle? Time by n pieces of Achilles' way will be t1 plus t2 plus t3 plus so on. This will be the time for Achilles t1, this one t2, t3 and so on. So t1 is for first part of the way, t2 will be 10 times smaller. T3 will be 10 times smaller than T2. T4 will be 10 times smaller than T3, and so on. So we have T1 1 plus 1 over 10 plus 1 over 10 squared plus 1 over 10 cubed plus so on. If Achilles runs 10 times faster than the turtle, he will chase the turtle, he will catch the turtle at the time 10 over 9 1000 divided by velocity. If velocity of Achilles is same as modern sprinter, we will get approximately 111.1111 in period seconds if velocity is 10 meters per second. So if velocity is 10 meters per second and we have 111 and 111 in period seconds, then distance traveled will be 1111.1 and so on meters. And this will be the distance, this will be the moment when Achilles catches the turtle. One more type of series is harmonic. 1 plus 1 over 2 plus 1 over 3 plus so on plus 1 over n plus so on, or sum n from 1 to infinity 1 over n. It's called harmonic because each next element is harmonic mean of previous one and the next one. So if we try to calculate this sum, we'll get sum k from 1 to n 1 over k, which will be greater than sum k from 1 to n integral from k to k plus 1 dx over x, because for every natural number k we have that integral from k to k plus 1 dx over x is less than 1 over k. So this will be bigger than that, and this will give us, this sum will give us integral from 1 to n plus 1 dx over x, which will produce ln x from 1 to n plus 1, which will be natural logarithm of n plus 1. So if we take limit of Sn, this will be infinity. So harmonic series is always non-convergent. One more interesting series is telescopic series. We have sum an, which is a1 plus a2 plus a3 plus so on, and this series can be represented as sum n from k from 1 to infinity bn minus bn plus 1 bk plus 1, where bk is some other sequence. So we'll have b1 minus b2 plus b2 minus b3 plus b3 minus b4 plus so on. So every element but for first and final will be cancelled. So partial sum will be b1 minus bn plus 1. So series will converge if and only if this bn plus 1 is convergent. Let's consider general properties of series. We can add up to series. Sum an plus sum bn will be just sum of an plus bn. Same for an minus bn. Also, if we multiply each element of some series by some number, this is the same as we multiplied all the sum by this number. So this is the first property, that sum alpha an plus beta bn can be expanded to sum alpha an plus beta sum bn. Second property, if we switch places, get rid of some elements or add some finite number of elements, this won't affect convergence of the series. So we have a1 plus a2 plus so on plus some alpha plus so on plus some beta plus so on. If we switch places of alpha and beta, so sum will be the same. So we will just have s minus alpha minus beta. But if s is finite, result will be finite. If s is infinite, then result will be also infinite. If we add some alpha and beta, again, if s is finite, then s plus alpha plus beta will be finite. But if s is infinite, then infinity will it be. Third property, if we have some convergence series, then we can group its elements in any way. So we can put brackets any way we want, as long as we don't switch places of these elements. And fourth property, that our series can be convergent if and only if the remainder is finite for every n. Because we have actually just s here and here, where s is sum an. So if we have Rn, we have Sn partial sum plus Rn. So Sn will be finite because we don't have any infinity here. It's always finite. But Rn is the part that will provide us with our required infinity if this series is non-convergent. Actually, removing Sn, considering property 2, won't affect convergence because Sn is finite. And there we have it. And we will finish today's lecture with necessary conditions of convergence and inconvergence. We have theorem that if sum an is finite, then limit an is 0 when n tends to infinity. So if series converge, then limit of an is 0, but vice versa is not always true. So if limit an is 0, it's not necessary that sum of n will be finite. Just remember the harmonic series. We have 1 over n which tends to 0, but sum is infinite. So how do we deal with the proof? Let us have s as sum an, then limit n to infinity, as n will be limit n to infinity as n minus 1 plus an, which will be s, because an is only one number. So from here we have limit n to infinity as n minus 1 is s, So limit n to infinity an will be limit n to infinity Sn minus nn Sn minus 1, but we have this number finite, so this Sn tends to S and this Sn minus 1 tends to S also. So for finite limits we can write them down separately. This will limit n to infinity Sn minus limit n to infinity Sn minus 1, which will be S minus S, which is 0. And there we have it, and limit is 0. And we have the corollary from this theorem. If limit n tends to infinity an is non-zero, then sum an does not converge.